Hello guys, welcome to PangeoHub. I'm Sujay, your mentor for the course of geochemistry. In today's class of stable isotope geology, let's discuss about basic theory of stable isotope, some common stable isotopes, and their use in geological systems. So, before any further delay, let's get started. Before stable isotope geology, let us first discuss about the isotope geology part. Isotope geology is an aspect of geology based upon the study of natural variations in the relative abundances of isotopes of various elements. Variations in isotopic abundances are measured by isotope ratio mass spectrometer and can reveal information about the ages and origin of rock, air, and water bodies or processes of mixing between them. So now let's come back to the stable isotope geology. So stable isotope geology is concerned with the variation of the isotopic composition of elements arising from chemical fractionations rather than nuclear processes. So it's a very important point to be noted that this stable isotope differs in the primary definition from the radiogenic isotope geology. So stable isotope, uh, the elemental variation appears because of the chemical fractionation rather than the nuclear process what we see in radiogenic isotopes. The elements mostly studied in here is actually hydrogen, lithium, boron, carbon, nitrogen, oxygen, silicon, sulfur, and chlorine. In some cases, also iron and calcium. Of these, oxygen, hydrogen, carbon, and sulfur are far most important. Before going into the applications, first we have to understand some basic points which these stable isotopes follow. One of these characteristics of stable isotopes is they have low atomic mass. Second point is the relative mass difference between the isotopes is large. Third is they form bonds with a high degree of covalent character. Third is the elements exist in more than one oxidation state. For example, carbon, nitrogen, sulfur from a wide variety of compounds, or they are important constituents of naturally occurring solids or fluids. For example, H2O, water, they consist hydrogen and oxygen. Both have very good stable isotopes. Last but not the least, and very important point is the abundance of the rare isotope is sufficiently high to facilitate the analysis. So it's very important point that the uh, abundances of the rare isotopes of these elements are somewhat higher in order that can be addressed by the analysis. So now let's come to the application part of the stable isotopes. We have seen that these stable isotopes can be used to identify or to get an idea about the intensity and temperature of post burial alteration of rocks. Even in the formation, temperature can be addressed. It is also helpful to find out the provenance of sedimentary clast, and it has a very good importance to find out the source of water samples. For example, the rains what we see in nowadays can be used to find out their sources. For example, uh, whether they come from some ocean or some lakes, some ponds, or a river body nearby. So we can address those kind of stuffs. In paleoclimate, we also see the stable isotope stratification, stratigraphy, and find out the paleoclimate. It is also helpful to identify the paleoecological conditions. Here in this diagram, we can also see that this volcanic degassing releases so much of sulfur, oxygen, hydrogen to the atmosphere, which mixes to the atmospheric gases and changes their value somewhat. Then there are terrestrial biological system which takes and releases some elements Then there is evaporation, evapotranspiration, as well as sulfate mineralization with the help of this hydrothermal vents, where these sulfur isotopic studies are very useful. And then there is biological intake of these marine organisms and releases as well. Then there is the subduction processes and upliftment processes. So as we can see, this there are various cycles going on in our Earth. So these stable isotopes are very useful to find out this processes and as well as this mechanism leading to this fractionation. Even in biological systems as well, the stable isotopes are readily used to identify the photosynthetic pathways, food webs, ecohydrology, nutrient cycling, to identify the human provenance. For example, someone living in lower altitude areas from someone living in the high altitude areas, their isotopic composition will vary somewhat. Then there is metabolic studies. For example, in the metabolic studies, the stable isotopes of hydrogen, carbon, nitrogen, and oxygen are used as stressors to describe body composition, uh, utilization of dietary nutrients, incorporation of dietary nutrients into body constituents, and other quantitative characteristics of growth processes. Then there are use of stable isotope in sports medicines as well. For example, this deuterium 2H is used as tracers, um, rate of ingested fluids, to find out these ingested fluids, how these ingested fluids are absorbed in the body. Then there is toxicology to distinguish between endogenous and exogenous biochemicals. Next, in environmental sciences as well, we know that the environmental forensing and monitoring to identify the source of pollutants, for example, in oil spilling cases, monitoring atmospheric gases to distinguish between natural and anthropogenic sources. Then climatic studies, this monsoon, climate, all those stuffs can be studied using the stable isotopes. Then there is water cycle research, what we just talked about. Then there is food authenticity and traceability, identify the adulteration in foods with cheaper food stuffs. So these stuffs can be addressed using stable isotopes. So as you can see, this stable isotopes has a wide range of use in even in our daily life as well. Now let's see how we can quantify this isotopic fractionations. The systematic study of the isotopic composition of light elements in the various naturally occurring compounds brings out variations which seem to comply with a purely naturalistic logic. These variations in isotope composition are extremely slight and are generally expressed in a specific unit. The unit is delta. Now we can see this here, this the thing delta here is not in percentage but in per mil. We'll see this. Now let's see the formula. Delta equals to sample isotopic ratio divided by standard isotopic ratio divided by standard isotopic ratio. So this delta notation is basically the isotopic ratio in your sample divided by your isotopic ratio in the standard minus 1 into 10 to the power 3. So it can also be rewritten as delta equals to sample isotopic ratio divided by standard isotopic ratio minus 1 multiplied by 10 to the power 3. Now this is actually expressed in per mil. The sign of per mil is like this. The percentage, then there will be similar thing like percentage, just zero. Now, as you can see, this is a relative thing with a reference to this standard. Now, ultimately this delta is a relative deviation from a standard expressed in number of parts per mil. Isotope ratios are expressed with the heavier isotope in the numerator and the lighter isotope in the denominator. So this isotopic ratio can be written as, for example, oxygen. Oxygen has we deal with this oxygen isotope and this oxygen isotope. So this is heavier, this is lighter. So this isotopic ratio will be somewhat like this. So 18O divided by 16O. This will be our ratio what we use. If delta is positive, then what we can say, then we can say the sample is richer in heavy isotope than the standard, right? For example, you are dividing this by this, the same thing of standard. So what we can observe, so this whole thing will become what? This whole thing will become, so if I write this in clear area, for example, as you can see, this delta oxygen, delta 18O will be what? This will be 18O divided by 16O in our sample divided by 18O divided by 16O in our standard. Sample by standard minus 1 into 10 to the power 3 per mil, right? So if this delta 18O is positive, then what we can say? We can say this ratio itself, this ratio itself is higher than 1, right? Because there is negative 1 associated with this formula. So it will be higher than 1. This higher than 1 means the heavier isotope is richer in the sample than the standard, right? This 18O, the presence of this 18O is higher in the sample than this standard, right? So this we can say about, so this we can say, right? So mark this formula. This is a very important formula. This generally comes in your exam. Now you can rewrite this equation again and again with respect to different elements, different isotopes. For example, we have written in here with respect to oxygen. You can write with respect to hydrogen, sulfur, chlorine, calcium, whatever. So if a question comes, uh, then you have to deal with this. Now let's see some questions. Now let's study a bit what a standard means. So we know that what is 1 meter. So who is the authority to judge what should be a meter? What should be the length of a meter? So there has to be some standard. So based upon which we can say this is 2 meter, this is 3 meter. 2 meter, 3 meter is nothing but twice the meter, thrice the meter, twice the length of a meter, or thrice the length of a meter, like this. So these standards are also like this. These standards are some laboratory specimens what we use as reference materials. So these reference materials are kept with very cautiousness, which based upon which we relatively say that this sample is enriched or depleted with respect to the standard. So let's see some basic standards what we use. For example, here are some ratios or some elements which are mentioned. Then there is the name of the standard and the description of the standards. So, for example, hydrogen ratio is mentioned uh, in terms of delta D, like this, delta D, which is basically deuterium deuterium versus protium. So 2H divided by 1H. The standard name is VSMO, that is basically Vienna Standard Mean Oceanic Water. Vienna Standard Mean Ocean Water. This is a bunch of ocean water kept in Vienna, Austria. So Vienna is the capital of Austria. Then there is 18O by 16O. The standard is generally VSMO, but we also can use VPDP. This VSMO is Vienna Standard Mean Ocean Water, what we have discussed. Then there is 13C by 12C for carbon. The standard name is VPDP, also known as PDB. That is, PDB is PD belemnite. So it's a fossil of belemnite from the PD formation in Canada. Then there is nitrogen, which is expressed as 15N divided by 14N. The standard name is air. Air is nothing but the atmospheric air. So atmospheric air is the reference material of nitrogen, whereas PD belemnite is the reference material of carbon, as well as in some cases as well as oxygen. We'll see why. And then there is 15 n then there is 34s divided by 32s. The standard reference is CDT. CDT is canyon diablo troilite. This canyon diablo troilite is a meteorite fragment from meteor crater in Arizona, which contains FeS mineral in troilite. So that is the reference material for sulfur. Now let's see a question. Whenever you see such kind of isotope related question, first break down the question and try to find out what is actually asked. So now let's break the question first. The question says the 18O by 16O of a quartz sample yields a value of 0.0019. The value of delta 18O of the quartz sample is what? Use the value of the ratio in VSMO as 0.002005. Now, what is given? The given things are what? So 18O divided by 16O of quartz sample is given. So our sample value of this is given, right? It is 0.0019. Now we can use this VSMO as this. So VSMO is nothing but 18O divided by 16O of standard. We have seen that. So the value is 0.002005, right? So what we have to do, we have to find out this delta 18O. We have to just use this formula. We can see this formula. So this formula states that what this will be 18O by 16O of the sample divided by 18O by 16O of the standard minus 1 into 10 to the power 3 per mil, right? So per mil don't need to mention in here because this is a NAT type question. So this value is given, this value is this one, this value is this one, and this value is this one, right? So we just need to divide. This is simple mathematics now. 0.0019 divided by 0.002005 minus 1 into 10 to the power 3. So let's find out the value. So let's take a moment and calculate this fast, everyone. So this value is what? This value is around what? Quick, minus 0.05236 or 5237, you can say, into 10 to the power 3. So it will be what? 1, 2, 3. So it will be 52 minus 52.37 per mil, right? So you have to see how many decimals are required. So you can adjust it accordingly. So it will become, so if we want to one decimal place, it will be what? Minus 52.4 per mil. Now let's see another question. So here it asks, oxygen has three stable isotopes, 16O, 17O, and 18, with average abundances of 99.756 percentage, 0.039, 0.205 respectively. The 16O divided by 18O ratio in a Jurassic limestone is 472.4335. In average seawater, the same ratio is 486.594. If average seawater is taken as standard, see, the standard is mentioned here. But if this standard is not mentioned, take the standard of V-smoke. What is the tell of the limestone in question? So let's see the question. Let's break down the question. So first you have to see what this this ratio and this ratio. So we have to find out what we have to find out what we have to find out this delta. Now it's a tricky question. Why tricky question? Because as you can see this one. So we cannot use this ratio in here. So we have to reverse this in our equation. Why? Because it is 16O by 18O what is given here as well. So we have to reverse this. So what will be the 18O divided by 16O? Right? 1 by this value, and for the seawater, obviously this one. Exactly. Now let's see the question. Now let this question is simplified. If you don't divide divide 1 by this value, your answer will be wrong. So here is the tip. You have to always see the ratio. Is it heavy by light, or heavier by lighter, or lighter by heavier? You have to always be careful about that. Now let's see the question. Now, so it's simple now. 1 divided by 16O by 18O of sample divided by 1 divided by 16O by 18O of standard minus 1 into 10 to the power 3 per mil, right? It's simple now. We can reverse this as well. We can write, if we want simple calculation, we can write this as well. So
So 1 divided by this and 1 divided by this. So we can write this up in here and it below this. So it will become what? It will become 16O by 18O of standard divided by divided by 16O by 18O of sample minus 1 into 10 to the power 3. So it will be the value of this 486.594 divided by 472.435 minus 1 and into 10 to the power 3 per minute, right? So this is coming around what? Let's take a moment and calculate this. It is 1.0299 minus 1 over 3. So minus 1, it will be 0.0299 and the answer will be close to 29.97 per mil. So it's almost close to 30. So have to practice this. So you have to write plus 29.97 or 30 per mil. Here as well, the minus sign, very important to note. In general sense, it is positive, but it's better to mention, right? So now we know how to deal with these questions. So now let's move on to the common isotope systems. So first is oxygen. Oxygen has three isotopes, 18O, 17O and 16O. Generally, we use the ratio of 18O divided by 16O to deal with the oxygen isotope systems. The oxygen isotopes are measured with respect to VSMO or VPDP. Typically, VPDP oxygen references is used for paleoclimates, while this VSMO is used for most other applications. So this VSMO is widely accepted one. So let's see why this there are two standards for oxygen, while there are only one references, only one main references for the other isotopes. So the point of the fact is this SMO is nothing but water, H2O. So there is oxygen. But this VPDB is nothing but belemnite. So this uh, belemnite has a cell which is calcareous. So calcareous is nothing but CaCO3. So in here as well there is oxygen. So this oxygen is also present as is present in this VSMO as well as this PDB. So in questions it may be asked that to convert the PDB into VSMO or VSMO to PDB. So we have to find a generalized formula to deal with this kind of stuffs. So the formula of this is like delta 18O PDB equal to 1.03086 delta O delta 18O SMO, what is SMO, 30.86. So this is the formula. The oxygen isotope is used in various places. As you can see, this oxygen isotope ratio varies from 5 to 12 in igneous and metamorphic rocks. In the carbonate, it varies from 7 to 34. In uh, diatoms, it is around 30. In sandstone shell, this is between 15 to 10 to 15. Then there is a huge range of for the fresh waters. Then there is a very narrow range in about zero, near about zero for oceanic waters, because VSMO is nothing but a mix up of various oceanic waters. So it generally lies close to this ocean water. So the atmospheric carbon dioxide is around here. The atmosphere oxygen is here. So as you can see, in various domains, we can use this oxygen isotope. Now let's see the principal use of oxygen isotope. Though there are various, but let's discuss this one because this is very important. Now, what happens? Oxygen has two isotopes. We know this. There is 18O and there is 16O. This 18O is heavy, relatively heavy than this 16O. So, whenever this evaporation occurs, what happens when evaporation occurs? It takes higher amount of lighter isotopes, leaving behind the heavy. So, when evaporation occurs, so a more amount of this lighter 816O will go into this, leaving behind this 18O in here. So that is why this evaporated or this vapor has a low number of delta, because in this the lighter isotopes are rich richer the lighter isotopes are more, actually the number of lighter isotopes are more than the heavier ones. Now it cools and it rains. When it rains, now this is a very interesting point. When it rains, so whenever gravity works, the heavier ones will try to go fast because they are heavier, right? So this first rain in here will be richer relatively in heavier isotopes, because they will tend to go to this tend to fall into the trap of gravity. So this will obviously make this cloud richer in lighter isotopes. So here we will find delta 16 or more in this cloud, more in this cloud, and delta 18O more in this rain. That is why this delta value is around -5, but this delta value of this evaporated water was -10. Now, when this goes further to the land in this direction, so obviously it will lose more and more heavier isotopes, leaving behind the lighter ones. So obviously, then this one will be, this rain will be somewhat depleted in heavier one and relatively enriched in lighter ones, right? So here we will find what this will be obviously enriched in 18O, but less enriched in 18O. But this cloud will be more and more enriched in what? 16O. That's right, in 16O. Now this, the final one here, right at the mountain, will be least enriched in heavier isotope and most enriched in lighter one. So in here, as you can see, this snow or this rain, whatever it is, this will be having the least number of delta value, right? So this glacier, which is forming because of this snow, which is having a delta value of -40, will also be having this one, because this glacier is nothing but this snow, nothing but made up of this snow. So obviously this glacier will be having a similar value of -40. So this glacier will be having more 16O than 18O, and this ocean will be having more 18O than 16O. This varies, this ocean water varies. The volume of ocean water is so large. This evaporation uh, doesn't even come closer to the volume of this ocean. So it varies near about zero, plus 5, -5, that's it. Nothing more. So as you can see in here, so it will be what? Around 2, 3. So plus minus 2, 3 around. So this oceanic compression will not vary much because of this so much enormous volume, but this glacier compression will. Okay, so obviously, as we have understood, this glacier compression will be having a very low delta value. Now, now this is very much related to this. Suppose we are observing our Bay of Bengal. A cloud rises from this Bay of Bengal and it starts raining in Puri first, then it goes to Kolkata, then goes to UP, Lucknow, then goes to Delhi, suppose. So these are the locations. So tell me here, this isotopic value will be more or less than Kolkata. In Puri, this delta value will be less or more in Puri. In Puri, it will be somewhat closer to zero, because here the fast rain will occur. So fast rain is occurring at Puri. So the value will be somewhat closer to zero, not much negative value. The value will be negative because there is evaporation. So evaporation in Bay of Bengal will take so much of lighter oxygen, leaving behind the heavier ones. But heavier ones will also be there. It is not like that I will only take the lighter ones, leaving every heavier ones. They will also contain the 18O, but the amount of 16O will be higher than the 18O in the cloud, because the evaporation will fractionate the thing, what we know as Rayleigh fractionation. Now here in the first rain, the isotopic value or the delta value will be closer to zero. Then in the next rain, the value will be closer to zero or very negative. Obviously, the value will go negative and negative again whenever it rains now on. So here as well, the value will be negative. From this, it moves here to Lucknow. So the value will be more negative and it goes to Delhi or Kashmir. Then it forms a snow. Then this snow layer will also be having a very high negative value, like this 40 in here. So obviously this glacier in here will also be having a very high amount of very high negative delta value, enriched in 16O than the 18. Now let's discuss about the glacial interglacial cycle. So in glacial interglacial cycle, what happens is, in glacial cycle so much glaciation occurs. So much glaciation means so much evaporation will occur. So much 16O will be moving out of the ocean water, forming the glaciers. So suppose in our world, in our earth there is, suppose, let's draw it like this. So in our earth, suppose this part is covered with snow and this part is covered with snow, and now in the glaciation period this part is also covered by snow here. So this covering is occurring more and more. That is why the ocean will be enriched in this one and depleted in more and more depleted in this one, and the glacial will be just opposite to this, right? So this ocean value of this will fluctuate in glacial interglacial cycle. When it runs through the deglaciation period, this glaciers will melt, and this water which is very enriched in 16O will move into the sea or ocean, and this will nullify the behavior or will control the 18O value, higher 18O value, and the sea will come very very close to this zero period or zero per mil value, not exactly zero but very close to zero. So we can see that glaciation deglaciation cycle can be addressed by this 18O 16O parameter, right? So you are understanding this topic. This is a very important part we have discussed. So you have to grasp this concept. This is very very important. How this glaciation deglaciation period is related with this oxygen. Now let us move to the isotopic systems. Next is hydrogen. So hydrogen has three isotopes: 3H, 2H, and 1H. This 2H and 1H are the stable ones, and this is not. This has a half life of 12.32 plus minus 0.02 years. So generally the ratio is 2H by 1H, and it is expressed as delta D. So this hydrogen standard is basically VSMO, and we can observe various things, various properties by using this hydrogen isotope, hydrogen stable isotope. For example, we can know about the meteoric water, magmatic water, metamorphic water, sea water, what is fresh water or not, depending on the hydrogen cycle. Then we can know about the Meteosonic ridge basalts, some granitoids, some detrital sediments also captured this hydrogen isotopic composition as it varies from this minus 100 to minus 40. So we can study a huge amount of things. For example, we can study about the petroleum products. Then we can study about the gases, for example, methane. We can study about methane. We can study about petrol, diesel, all the petroleum stuffs. Know their sources, know their fractionation processes. So all these stuffs can be used, can be addressed by using this hydrogen isotopic system. The major use of this hydrogen isotopic system is just like the oxygen. To use this, we know a very important concept that is called the global meteoric water line. So the global meteoric water line describes the global annual average relationship between hydrogen and oxygen isotope, that is oxygen 18 and deuterium. This ratios in natural meteoric waters. The global meteoric water line was first developed by Harmon Craig in 1961 and has subsequently been widely used to track water masses in environmental geochemistry and hydrogeology. So as you can see, this the very important part of this of the use of this hydrogen isotope uh, lies in this environmental geochemistry and hydrogeology part. So as you can see, this formula is very important. You can note it down. This delta D is nothing but the stoichiometrium, and this equal to 8 into delta 18O plus 10. So it gives an approximation about the global meteorite water where it lies. So this is a very important concept. So any meteoritic water, you can uh, track this, if, whether it lies in the range or not, or whether it is an isolated system, isolated water body. So this is a very important relation between oxygen and hydrogen isotopes. Now let's go to carbon. Carbon, as we know, all the organisms are made up of carbon, and carbon is a very important one, a very important isotope to be dealt with. So carbon has two stable isotopes, 12C and 13C. So the ratio is generally expressed as 13C by 12C, and the standard is measured relative to PDB, that is PD belemnite standard. So this carbon 13 carbon varies from this around 15 to 35, 38 in sedimentary or petroleum, coal, organic materials. Then the variation is expressed here in terms of bar diagrams for marine and non-marine organisms, the freshwater carbonates, marine carbonates, air carbon dioxide, and carbon carbonatides and diamonds. So as you can see, carbon isotopic ratios vary so much, and this makes the carbon a whole system that is very useful to study this mechanism process to identify these sources. We can also study a whole lot of stuff. For example, in organic chemistry research, studies into molecular structure, metabolism, food labeling, air pollution, even in climate change as well, we can study this one, this C13 value. Even in stromatolites, this is heavily used to identify, to use it as a paleoclimate indicator. They have a huge use in C4, C3 plants as well. Now let's move to nitrogen. Nitrogen, as we know, is the most abundant gas in our atmosphere. So nitrogen has two stable isotopes, 15N and 14N. Nitrogen ratio is generally expressed as 15N divided by 14N and are measured relative to the atmospheric nitrogen. So this is generally showing the geological the application in geological systems. So in atmosphere, this nitrogen is very close to zero. The ocean water, it varies like this. In sedimentary rock, it is generally in negative. It is in the negative part in the metamorphic rock as well. The basaltic rock, it varies. The nitrogen varies, and in diamonds, it is generally positive. So nitrogen has a very important role because we know about the ammonification, denitrification, nitrification, the the absorption of atmospheric nitrogen into organisms, into soil. Then there is denitrification as well. Then there is ammonification. So if we try to draw a sketch of this nitrogen cycle, so in atmospheric oxygen, so in atmospheric oxygen, atmospheric nitrogen, this delta value is close to 0 per mil. then it is absorbed in the ocean. So it is basically the ocean. So the upper layer of the ocean is oxic. So it will be dissolved in nitrogen. So it is dissolved nitrogen. So here the value is around so delta 15N is close to 0.6 per meter. So it goes through fixation process, nitrogen fixation, and the delta 15N value becomes close to plus 5 per mil. Then there is ammonification process of this one. So this ammonification process, this ammonification process changes this uh, isotopic ratio to about 0 per mil. This is basically ammonia H4. It also supports nitrification. So in nitrification, what happens is this nitrification, this this becomes NO3 minus, and the change is around this change is around 16 per mil. So it's plus 16 per mil on this one. So then it also then it suffers denitrification, denitrification, and it goes to this N2. Then there also might be this assimilation thing which goes to this one in here, and this fixation can also go into this organic matter where this nitrogen is absorbed in the organic matter where this value is somewhat close to 5 as well. Then it might also suffer diagenesis where it becomes NH4 plus, where this delta 15 in value becomes somewhat closer to 7 per mil. So this is here is the oxic anoxic line. So this is a very crude diagram showing the variation where we want where I wanted to show the variation of the isotopic compositions of nitrogen. These isotopic compositions, this is all about the nitrogen cycle. So these isotopic compositions may vary from book to book. So this is just a crude diagram showing how this nitrogen cycle behaves. Now moving on to the sulfur. Sulfur is very important even in sedimentary rocks and in the hydrothermal systems as well. So sulfur has four stable isotopes: 32s, 33s, 34s, and 36s. So the ratio is generally measured relative to canyon diablo troilite meteorite, as we have discussed. It has a very wide range for sedimentary rocks, as the sulfur composition varies in sedimentary rocks. In the granitoid bodies, it is generally negative. and even in basaltic rocks as well. In the metamorphic rocks, this sulfur isotopic ratio varies from -20 to +20. In the evaporite, it's generally negative. Sulfur is a very important in one sense that pollutant identification. Now moving to the silicon. Silicon has three stable isotopes, and as we know, we deal with the silicate rocks, silicate minerals. Uh, so silicon has three isotopes: 30 Si, 29 Si, and 28 ACI. Silicon ratio are measured relative to NSB28. That's a standard. It is also known as NIST RM 8546. That you don't need to remember, but this is for your knowledge. And the silicon uh, content varies, where it is generally positive for the mafic igneous rocks, and the felsic rocks varies. In the ocean water, the silicon is generally negative. So that is all about the traditional isotopic system. There are many more that you can study on your own. That there are Fe, Ca, then there is chlorine. So all those stuffs are there. So it's all up to you to explore all the stuffs. So this is all about the basic isotope uh, concepts. And one more thing, and some more things I want to add that generally comes in the questions, that is characterization of isotope variation. For example, between two geological products, for example, A and B, which are related with a natural process and whose isotopic ratios, for example, are written as Ra and Rb. So their ratios we can write as alpha A B equals to Ra by Rb. Now, from the previous equation, we know that this delta is nothing but the ratio of uh, isotopic ratio in sample by standard. So this sample by standard is nothing but R in here. So minus 1 into 10 to the power 3. So if we rewrite this equation in terms of this delta, so R will become R equals to delta divided by 10 to the power 3 plus 1, right? So we can use this formula in here and in here, right? So this alpha will become delta 1 plus delta A divided by 1000 divided by 1 plus delta B divided by 1000. So by following this mathematical notation, what we know previously from our math classes, that here if 1 plus epsilon divided by 1 plus epsilon dash is there, we can rewrite this one as 1 plus epsilon minus epsilon dash. So if we follow this in here, so it will become what, 1 plus, so better we write it like this, not exactly but somewhat, is delta A minus delta B divided by 1000, right? We note that this delta A B is nothing but the expression of this difference, del A minus del B, right? This is nothing but the difference. It here it can be rewritten as like this. So this is nothing but just a difference between delta A and delta B. So we are using this instead of this to simplify this equation and to reach to a very validated equation of stable isotope geology. So if we use this one instead of this one, so the equation will become what? Alpha equals to 1 plus del capital Del A to B divided by 1000, right? So 1000 AB, 1000 alpha AB minus 1 equals to del AB. It is possible then to calculate the overall fractionation factors for various geological processes. The transition from granite to clay by weathering, the evaporation of water between ocean and clouds, the exchange of carbon dioxide in the atmosphere with that of dissolved in the dissolved in the ocean, or with the carbonate with the carbon of plant, and so on. So we can use this various processes in here. So we have seen today the basic theory of stable isotope geology. We have discussed about different isotope systems and their applications. So that's it uh, from today's class, and we'll see you in the next one.